Hey guys, this is the Integrated Science. We're in the Chemistry Unit 3, Skill 2, Types of Matter. So this is part 1. We're just going to introduce the different types of matter. Last skill in Unit 3, we discovered what matter is. So now we're just going to classify it a little bit. So first thing we have is pure substances. So if you're looking at a pure substance, then there are two options. And you're going to look at the atomic level for these. So the first option is it could be an element. So if you have an element, then all of the atoms in your sample are going to be the exact same identity. So for example, a helium balloon. If you have a helium balloon, pure helium, then inside that balloon, every single atom is going to be a helium atom. And that's what makes it an element, is that all the atoms are exactly the same. And that's what makes it pure, is because it's all exactly the same, or it's pure. There's nothing different. And as we saw before, all known elements are listed on the periodic table. So if there's a question that says, is this an element or not, or if you're identifying it, the very first step is to just peruse the periodic table and see if it's there. So for example, if I say zinc, is that an element? You can look right here and see, boom, on the periodic table. Versus if I say glucose, when you look through the whole periodic table, there's nothing that says glucose, so glucose is not an element. The thing that makes elements elements is they can't be broken down into simpler substances without losing chemical properties. So let's go through a couple elements and discuss some properties. So first, gold, for example, at room temperature, gold is a solid. It has a golden color. It is shiny, it can conduct electricity, and if you break it down past the atomic level, it won't be those properties anymore. It's not going to act like gold anymore. Chlorine, for example. Chlorine, room temperature, it is a gas. It is a green gas. It is very infamous for being poisonous. It is used in chemical warfare, so that's why we're not going to have that in the classroom. But chlorine gas is green, it is toxic, it is painful as soon as it hits the airways. So if you breathe it in, it's instant pain in your nose. So obviously these two are very different because they're different elements. Bromine is a liquid at room temperature. It is the only non-metal that is liquid at room temperature. And it is brown. It has a very thick vapor layer above it, so that's why you see all this gunk on the outside. Mercury is an element, so all of the mercury atoms are exactly the same. Mercury is the only metal that is a liquid at room temperature. Mercury is infamous for causing Mad Hatter syndrome. So it can be absorbed into your bloodstream and nervous system, and then once it gets to the nervous system, it causes severe sickness. Mercury poisoning. They used to use mercury as teeth fillings, metals, because metals are malleable, meaning they are shapeable and strong, but mercury is even cooler because it's liquid, so you could just pour it into the hole in the tooth. But that ended up making people go crazy and lose their hair and get very sick. So they no longer use mercury in tooth fillings. It's called Mad Hatter syndrome because people who made hats used to use the mercury and they would spread it over a feather, and the liquid would actually pull out impurities in the feather. So hatters, people who made hats with big feathers back in the day, they used a lot of mercury and they would go crazy. The next type of pure substance is a compound. So in a compound, all atoms are bound together in a constant pattern. So for example, water is a compound, and you can see these molecules are always the same. It's H2, as in 2 hydrogens, and O, 1 oxygen, and you're seeing the same thing over and over again. So if you look at just the things bound together, they're exactly the same. That's what makes it a compound. So pure water has only H2O molecules, 2 hydrogens, 1 oxygen. If you ever have a sample of pure water, it will always be H2O. You can't have anything else. If you do, it's not water. So it always on the atomic level is always the same. That's what makes it pure. Compounds have a chemical formula. So if there is a set ratio of the number of atoms, see this H2O, that's a chemical formula. If there's a chemical formula, it's definitely a compound. Compounds are made of elements bonded together in a specific pattern. So that specific pattern I'm talking about for water would be H2O. And if I look at each of these little guys, I've got 2 hydrogens, which are shown by those red circles. And if you notice, all of these have 2 red circles, or 2 hydrogen atoms, and they all have 1 oxygen atom. So because they have that specific pattern, it's never changing. All samples of a pure compound, a pure substance compound, are always going to be the same chemical properties. So compounds do not maintain the properties associated with the elements that make it up, right? We just saw water. Water is made out of hydrogen, which is a gas, oxygen, which is a gas, and when they come together to make H2O, you suddenly have a liquid. So you're not keeping the same chemical properties once you become a compound. So there's water. Silver oxide is this powdery black powder. You know, silver is silver color, oxygen is clear, and they come together to make a solid powder. Or ammonia, something you clean with, NH3. Ammonia has a really powerful, potent smell if you've ever cleaned with it, versus nitrogen is 77% of the air you're breathing right now, which has no smell. Hydrogen is a big component of the air you're breathing, no smell. They're both gases. When they come together, it's a liquid with a potent smell. Compounds are formed when atoms or elements are chemically bonded together. So there's literally the electrons on the outside of the atoms are interacting with each other to make them physically linked or chemically linked at the atomic level. So when you look at the chemical formula, the subscripts after the element tell you how many atoms of each element are present in a molecule or formula unit. So if there's no subscript, you can just assume that there's one atom. So let's do an example. So sodium chloride, NaCl, you have no subscripts. And by subscripts, I mean the numbers that are below. So sub means below, so look for the little numbers at the bottom. So here is NaCl. You'll see that there's one sodium and one chlorine. And the thing about it is there are a bunch of them. So you're not just going to have one formula unit in a sample, you're going to have a whole bunch of them. But if you notice, for every one sodium, there's always one chlorine. So you keep repeating that pattern of 1 to 1 for sodium chloride. For sulfuric acid, H2SO4, so here is a molecule of sulfuric acid. And you can see that you have 2 hydrogen atoms, shown by the 2 here, 1 sulfur atom, and 4 oxygens. And you can see that over here as well. And that's always going to be like that. If you have sulfuric acid, it always, always, always has that ratio. And that's what makes it pure, is that every single molecule of sulfuric acid is always the same. So there's another thing you want to look for reading chemical formulas, and that's parentheses. Parentheses group atoms together, and any number outside the parentheses gets distributed in because it's saying you have that many of everything inside. So for example, aluminum sulfate, Al2, parentheses SO4, and parentheses 3. So this would just be Al2SO4, but it actually looks like that because you have 3 SO4s. So if I were to count these up, you can see I have 2 aluminums. These big blue ones are the sulfurs. I've got 3 sulfurs and then 12 oxygens. So 2 aluminums, 3 sulfurs, 12 oxygens. That's it for pure substances. The other type of matter is going to be a mixture. So when looking at a mixture on the atomic level, it's made of 2 or more pure substances. So if you look at this, what we have here at the atomic level, you can see I've got this Mickey Mouse looking molecule, and then I've got this big guy over here, and I've got another here. So I've got multiple different things at the atomic level, so that's what makes it a mixture. Most matter is a mixture. The desk you're sitting on is probably a mixture, unless it's like a pure wood, but there'd still be screws or something in it, so that's a mixture. The calculator that you use is a mixture. So mixtures are made by physically combining pure substances. All right, so here I've got whatever this liquid is, whatever this liquid is, as soon as I pour them together, it's a mixture. Mixtures can be broken down into their pure substances by physical means, as in not changing bonds. I could have a sample of jelly beans and pull out all the green ones and keep all the red ones. I have just separated that mixture, and it didn't take any chemical process. So there's 2 types of mixtures. We have homogeneous and heterogeneous mixtures. Some people say homogeneous. I've always been told homogeneous. So, okay, let's go talk about each one. So a homogeneous mixture is made out of 2 or more pure substances, but there's only one phase when looking at it. And by phase, I mean everything looks the same. That's the one phase that it has. So for example, tap water. If you look at a sample of tap water, no matter where you look within the tap water, it all looks exactly the same. And the prefix homo means same. So homogeneous looks the same throughout the mixture. Honey is a mixture and it looks the same throughout. So if you take a sample of honey and you pour it and you keep looking at it, it's all going to look the same. Pudding is a homogeneous mixture. Mixtures do not have to be liquid. I mean, pudding is liquidy, but it's not fully liquid. Anything that says a solution, so say you have a hydrochloric acid solution, that typically means it was mixed with water. It could have been mixed with other things, but generally water is the most common solvent. So if you ever see the word solution in chemistry, you know that it's a mixture. The other type of mixtures are heterogeneous mixtures. So heterogeneous mixtures are still made out of two or more pure substances, because that's what makes it a mixture, but they also have two or more visible phases, as in you can see distinct parts of it that are made out of different things. So you can see in this picture here, I've got one phase up here where these molecules all look the same, and another phase over here where the molecules look the same. So for example, pizza. Pizza is a mixture, right? It's got multiple things in it. Check out that. That's got beautiful. You got pineapple, you have ham, you have cheese. All of those are different things, and you can clearly see the difference between them. So there are different pieces. The prefix hetero means different. Anything alive is going to be a mixture because your cells are made out of different pieces in it. So anything living, for example, this cute, adorable puppy, that's a heterogeneous mixture. You're a heterogeneous mixture. If you have some blood spilt, then that blood is a heterogeneous mixture. Muddy water, clearly you can see the phases. You can see the water down here and the mud separating, so that is heterogeneous. So when talking about the types of matter, here are the 4 types and the 2 branches that we discussed today. So this is kind of a handy dandy tool to use. So you can see right in the center on top, matter separates into pure substances or mixtures. So pure substances, to tell the difference, look at the atomic level. An element is going to be on the periodic table and it has all the same of the atoms, so though it's drawn by circles here. A compound has multiple atoms bound together, but all of them are exactly the same. A mixture, however, is going to have different things in it. So if you look on either side of the mixture, you don't have the same substance always, but a homogeneous mixture has this different stuff throughout versus a heterogeneous mixture has one set type of thing here, one set type of thing here because it has different phases versus the homogeneous mixture is the same looking throughout from the macro scale or the human scale. So good luck on identifying types of matter. Let me know if you have any questions and I will see you in the next set of notes.